And welcome back. In this video, Lee is going to begin implementation part 1 for Perlin Noise 2D.
All right, this one will be the easier of the two implementations, mostly because we're going to be doing a lot of copying and pasting. But I do need to include the Unity engine into my using statements. So I will add that now. Now, the reason why I'm going to copy and paste this is, one, it's a lot of numbers and it would take a very long time for me to type this, and I don't think you guys want to sit here while I type all of those numbers for the next couple of hours and hope I get them right and spend a couple more hours debugging them when I mess it up. But basically what we're doing is we've got an array of vector 3s. We're calling it grad3, and this is the array that is holding each one of those vectors that we were talking about, the ones that go from the center of the unit cube out to the midpoint of those edges. So these are the definitions for those vectors. If I jump back over into here, these are the vectors that are defining, or the definition vectors that are defining this shape. So we're going from the center out to each one of the midpoints on each edge of the unit cube. So that's all these are defining. So that's those. Now this next really large array is simply the numbers 0 through 255 generated at random, and there's no repeat. So each number appears in this array a single time from the number 0 all the way up to 255, which, is in here somewhere. I'm not going to go find it. It'll take too long. Well, actually, I can find it.
Now, let me ask you this. Is this something that you copied out of his thing, or did you just randomize the numbers yourself?
You can randomize the numbers yourself if you want to. It's not going to hurt anything. But these were copied directly out of the Simplex demystified paper.
Okay.
So they are copied in their entirety. But they are just the numbers 0 through 255 in random order with no repeat. So if you want to generate your own, feel free to. It won't hurt anything. Your results will just vary a little bit from what we have. The next thing that we're going to do is create another private static read-only int array, and this is going to be called perm. It's going to equal a new integer array of 512. What we're doing is, instead of typing all these numbers twice, we're just going to create another array, and then we're going to populate it with this array repeated twice. And we'll do that inside of the constructor. So inside of the constructor, we'll just go for int I equals 0 through 512, because I know there's 512 elements in that array. I could also do perm.length. Either one will work, whatever you prefer. And we're going to set each element inside of the perm array to equal its counterpart element in the P array, but we're going to mask it with the number 255. This is going to make sure that we're not exceeding 255. So if we hit 255, the next element begins 0 again. It's kind of like a modulus in that way. I don't need these brackets. So that will set up our initial permutation array. Now, we have a floor function here. I'd like to add one more function, which is going to be a private static, going to return a double, and we're going to call this one fade. This array, or this method, sorry, got array stuck in my head, but this method is going to take in a double, and it's going to calculate out our gradient. And the gradient is a function of t times t times t.
Times.
Yeah, I'm working on it. Well, every once in a while I do look up at the monitor to see what I'm typing, and then I realize I made a mistake. So 3t's multiplied by t times 6 minus 15 plus 10. Now, this really weird looking equation, again, if we jump back over to our paper, and I scroll up, is this equation right here just unrolled. So this is the calculation that is being used to calculate out our gradient, but instead of using the power functions, which can be fairly slow, we just unroll it into this form. So it's the same thing, just a little bit faster. And one of the little tricks that you can do for optimization, I'm just putting it here because we'd be using the same line both a couple times in the 2D implementation as well as a couple times inside of the 3D implementation of Berlin noise. But if you wanted a little bit more optimization, you can actually take this equation and inline it instead of calling this method. That will get you a little bit of performance back. So, but for readability, I'm breaking this out. That's going to be true with most of these noises. What I'm coding that you guys are watching are not the most optimal way of doing things. They're here more for readability, so you understand, or make it easier for you to understand and figure out how these noises are being created. Once you understand the basic concepts of them, then you can go back and optimize them any way that you want to make them faster. So this is the base implementation that I wanted to cover in this first implementation video. In the next video, when we come back, we're going to create the actual Perlin noise CS file, and we'll implement that part of the noise class that will actually calculate our 2D noise.
Okay. So with that, that's going to conclude this video. Thanks a lot.